machine can move, a robot can adapt. The difference is not just the arm, it is the motion control stack that ties motors, encoders, gearing, and kinematics into one coordinated system. Today, we are breaking down integrated motion control and why it is the quiet upgrade that lets robots do precise, reconfigurable moves inside real work cells with conveyors, vision, and other automated machines. Here is the key contrast. Conventional machinery is usually designed for one well-defined task in one fixed location. Robots, on the other hand, are built for complex, programmable sequences that can be reconfigured for new jobs. Even the formal definition is broad. ISO 8373 describes a robot as an automatically controlled, reprogrammable, multi-purpose manipulator with 3 or more axes. That axis count matters because it is where coordinated motion begins. Now, the fun part. Different robot types, same core problem. You need multiple axes to hit a target position and orientation, and you need the controller to coordinate them without jitter, drift, or timing gaps. Cartesian robots are basically precision linear motion systems, guides, screws, encoders, or even linear motors. They are modular, common in packaging, and they look simple until you need all axes to arrive at the same time. Delta robots, the spider-like pick-and-place champs, bring their own kinematics and dynamics. Industrial deltas often run permanent magnet servo gear motors on each linkage, chasing speed while keeping vibration under control. Gear choice is not trivia here. Helical gearing can help reduce vibration, while planetary gearheads are popular because they pack lots of power density into a compact volume, a big deal when the gearbox has to fit inside a joint. 6 degree of freedom arms are what most people picture. But repeatability at the end effector is not constant. It depends on where you are in the work envelope. At full reach, accuracy typically gets worse, so layout and path planning matter. Think of it like this. A straightened elbow puts the wrist far out, but you lose orientation flexibility. Keeping tasks well inside the arm's reach can improve effective repeatability and reduce the need for aggressive control compensation. Scara robots sit in a sweet spot, 3 or 4 axes, fast pick and place, and strong performance in lab automation. They are often delivered as off-the-shelf systems, but the kinematics are simple enough for in-house builds too. Industrial Scaras commonly use AC servo motors with absolute encoders. That is huge. Position feedback can persist even when power is cut and restored, which reduces homing time and makes the cell easier to recover after stops. And the mechanical design choices show up in the Z-axis too. One example discussed is a belt-driven Z-axis with 2 linear guides, a different trade than a classic ball screw, tuned for packaging-like motion profiles. Zooming out, the article's theme is integration. Reduce latency, reduce wiring and tuning complexity, and reduce cost. In a mixed work cell, you are synchronizing multi-axis motion with robot kinematics, plus conveyors and vision timing. So what are the real-world alternatives? In many factories, the short list is PLC-based multi-axis motion control, like Siemens Semantic with Synamics drives, Rockwell Automation Control Logics with Kinetics, or Beckhoff TwinCat with AX servo drives. All can run synchronized axes, but integration depth changes commissioning time and performance. If you're tech-savvy, here's the takeaway. Integrated motion control is not just about speed. It is about deterministic coordination, repeatable behavior, and faster deployment across robot types, Cartesian, Delta, Scara, and 6DoF, with fewer surprises at the end effector.